This lesson, we're going to talk about some problems that can arise in pipeline design. And potentially, with considering a pipeline design, we can have instructions that can result in inefficient processes or hazardous processes. And so we call these processes that are result in inefficiencies to be hazards. And so there are three types of hazards that we are going to consider. We'll consider structural hazards, which which occur as a result of data path and resource limitations. We'll consider data hazards, which result as a result of program limitations. And then we'll consider also control hazards as well, which also can result from program limitations. And these can essentially cause our hardware to take more cycles than necessary to complete a instruction or data path. And so let's consider our sandwich shop example again. So let's say we have Bill, and Bill has his workers that are working diligently for him to arrange and process all of the sandwiches. But Bill has a new idea that he wants to add a new option for customers. And so in this, what Bill wants to do is allow for customers to order fries. And so Bill thinks that since the cheese guy has the less amount of work, maybe the cheese guy can add fries on the side for customers. So what type of problem might this present for us? So in this scenario, if the cheese guy needs to get the fries as well, this has to result in the cheese guy taking a break from his work. And so this can result in inefficiencies because now, as he has to get the fries, this can result in work being stopped. And so now we have customers customers that are waiting for their orders to be taken, and then customers or workers that now have no more orders to process. So this results in some workers not having work as station 3 has to go get the fries. And so we'll have what we call a break in our cycles, as no work is occurring for station 4 and station 5 during this process. And so this results in what we can call a stall. So if we do allow for the cheese guy to add fries to some of the orders, then what exactly will happen? Does the pipeline continue to produce one sandwich per clock cycle? Does the pipeline produce more than one sandwich per clock cycle? Or does it produce less than one sandwich per clock cycle? And really with this in effect, this is going to decrease productivity, and really, so option C, it's going to produce less than one sandwich per clock cycle. And so this presents a problem for us in that we have a structural hazard, and because we do not have enough resources in place in order to accommodate the station 3 accounting for both the cheese as well as the fries. And when we have this in place, we call this a bubble in the pipeline. And bubbles are basically going to reduce efficiency because it results in somewhat of an empty instruction. And so let's consider another example with our branch of equal instruction. Now, it's important to keep in mind that with BEQ, it's going to need to do essentially these two arithmetic operations. It's going to do A minus B, and then it's going to need to add to the PC. So where is this going to mean trouble for us? When we consider the process that needs to take place, we'll need to consider when we'll need to let each previous stage know that we need a pause. And this can be done using feedback lines. So at this point, we have our branch of equal instruction. And in order to execute, it's going to need to use our ALU twice. So what this means is that we can tell the first two stages that we need for them to hold off or to wait until we have continued the process. And so we have a no op instruction that gets passed to memory as well. And then we have a no op instruction that is also passed to write back. So this results in inefficiencies. And so we need to figure out how we can improve these inefficiencies. Well, we can have another option, and that is that we can incorporate more hardware. And so now at station 3, instead of us just having a cheese guy there, we're going to have a fry guy there that can, so both can operate together if needed, or one or the other. And so what does this mean for our BEQ instruction? We can incorporate a second ALU to do the operations in one cycle. And so this allows for both of the operations to occur during the execute stage. And that way the ALU can handle either computation that is needed. And so now, considering what we've been able to review based on pipeline structural hazards, what can be the cause of structural hazards? Do branch instructions in the program cause it? Do load instructions in the program cause it? Is it caused by data dependencies in the program? Or is it hardware limitations in the data path? And so for our example, the way that we were able to solve our structural hazard was by adding additional hardware. So we can note that it can be hardware hazards that cause the problems with structural hazards. So this is just one example of how you can easily alleviate inefficiencies that are caused by structural hazards. We also have a hazard called a data hazard. And a data hazard can occur when you have a data dependency that exists between successive instructions. And so here we have two instructions, 1 and instruction 2. And instruction 2 is going to need to read data and store into from register 1 into register 4 at the same time that it is being written to R1 in instruction 1. And so this represents what we called a read after write data hazard. In this case, we have the two instructions that are occurring right after each other. And so there's a data dependency that exists between these two instructions, in which one can't execute directly after. In this case, we have instruction 2 is writing a new value to a register while it's being read from instruction 1. The hazard that can also exist is a write after write data hazard. And in this case, we have instruction 2 is writing a new value to the register, and it's also a target of the previous instruction. So these are some different types of data hazards that can occur based on how instructions depend or share data. So let's take a look at our read after write data dependency. So in this case, we have R1, a value being written into R1, and then R1 needs to be read by instruction 2. So at this point, we have R1 hasn't even been computed, but instruction 2 needs it. So in order to mitigate this, we're going to have to stall the pipeline here so that the execution of I2 isn't inconsistent. So in order to fix this, we'll introduce our no-op instructions. But we'll need specific hardware that will enable us to know exactly when we can introduce these bubbles or no-op instructions. And so we're going to add a bit to our register file known as a busy bit. And the busy bit is just one more additional bit that we add, and it can be used to designate whether we need to declare a no-op instruction. So the IDRR stage will set the busy bit and will require that the write back stage have the responsibility to clear it when necessary. So this results in when I2 gets to IDRR stage, it'll find the busy bit is set for R1, and then it will need to stall. And then once 3 cycles have completed, the busy bit will then go away. And so let's walk through the example to see how this occurs. In this stage, we see in cycle 1 that we're reading into our instructions from the register file. R1 is not ready to be read just yet for instruction 2. So our busy bit is set. In cycle 3, a no-op is passed into memory. And then in cycle 4, a no-op is passed. We needed 3 no-op instructions in order for R1 to be ready to be read. And so another consideration that we want to keep in mind is what would happen if we were able to move later instructions in between our original instruction 1 and instruction 2. And so now we have a new instruction 2 and a new instruction 3, and our previous old instruction of 2 is now instruction 4. So what happens to our data path if we were to insert these 2 instructions between the definition and use of a register? What will this help our case and reduce the number of bubbles or add additional bubbles? And so if we insert 2 instructions to allow for separation between register 1 being defined and register 1 later being used, will we continue to have 3 bubbles in the pipeline? Will it reduce the number of bubbles to 0? Will it reduce the number of bubbles to 1? Or will it reduce the number of bubbles to 2? So you want to go back and and consider that the two instructions do not depend on write values that are being written from R1. And so they can still occur. So this means that it'll allow for us to reduce the number of bubbles from 3 down to 1. And in order for this to be done, it would need to be something that is handled by the compiler. So this is a good trade-off in which that you want to ensure that the compiler can optimize the application code to mitigate any data hazards like this. It's a bit of a trade-off because the hardware will also need to be able to accommodate other hazards, but smart compilers should be able to handle read after write data hazards. And so if we were to consider how this would occur in our waterfall approach for each cycle for our 4 instructions, we see that the instructions can execute down the pipeline but once we get to instruction 4, there's a stall that occurs of just 1. And so this is one way in which we're able to reduce inefficiencies in our programs. And next we'll discuss other approaches that we can take to limit, to eliminate the bubbles by throwing in additional hardware constraints.